sampling type estimators based on approximate marginal MCMC. Thank you.
Okay, thank you. And thanks, AJ, for organizing this and inviting me. It's really a pleasure to be here. So this is joint work with my former postdoc, Joni, who is now in Linköping, my PhD student, Jordan, who is here, and then some more recent work with AJ and Cody as well. Right, and basically what I'm going to talk about is inference for latent variable models. We've seen latent variable models in this meeting several times before, and this is no exception, so there will be more. But that's an important class of models, and we want good inference algorithms for that. And then I'll talk about some existing inference algorithms for that class of models. Which are popular or used a lot in practice, and basically then I'm telling what we suggest that might be actually a good idea. So in some sense it doesn't bring much new because it uses basically the same building blocks that have been used before in those popular inference algorithms, but it's sort of a repackaging of the ideas in a way that I haven't seen used much, but it can actually make practical sense, or sense in practice a lot, or can be useful. And then there are some examples which we tried somehow, where we tried our approach and compared to the alternatives, and then there will be a bit of discussion. Okay, so what's the class of models? This is an abstraction of various interesting statistical models, and I'm keeping it fairly abstract, but basically it's sort of a model, joint model of three variables, theta, x, and y, which I call hyperparameters, latent variables, and observations. And the last one is obvious because the observations will be basically observed. So we observe only the value for the random variable y, and I call the observations y star. And then basically theta and x both remain unknown, and we want to do Bayes inference. Right, and basically we have joint laws, we have conditional laws for those guys. So we have some prior distribution or prior density for the hyperparameters, and then a joint distribution for the latents and the observations given each hyperparameter combination. And often you have much more structure in the model, but it's not so relevant for this talk, so I can keep this rather abstract. So we basically just we are interested in pi theta x, which is proportional to prior of theta and then a joint of x, and then we have the observed values plugged in. Right. So this is what we care about. We would like to do inference with that kind of a setting. Right. And here's an example which you've seen a couple of times in this meeting before. So it's a stochastic volatility model. So theta is a vector of 3, contains phi, sigma x, sigma y, 3 parameters, and basically 2 of the parameters are actually parameters of the latent variable part, which is a priori assumed to be stationary Gaussian AR1. And there's a simulation in red of the x, the AR1, with certain parameters there, with a 200 length of 200. And then basically the observations just follow again a Gaussian distribution, and actually even a zero mean. In this case, this is a simplified model, but the variance changes. Basically, it depends on the current value of the latent variable x. So the higher x is, the more fluctuations you see in the output there. So y is here in black. And the point is that we only see that black thing, which I've been told this model can be used to model stock market data, so that those black things are daily returns. But I haven't really done so. But, this is sort of close to being practically relevant model, if not already relevant in practice. But it captures certain features of these latent variable models, which I sort of want to emphasize. And what are those? Basically, in many cases, the hyperparameters are actually, they live in a low dimensional space, or there are only few hyperparameters. Like in that example, we had 3 hyperparameters. But the latent variable space is large. And it doesn't mean that that's, like in this case, this is actually, so each value of x is scalar. But the point is that actually the latent space is the whole sequence of x's of length 200 there. So basically that makes the distribution high dimensional. Well, this is not really high dimensional here. It's 203, which is at most moderate, I think, these days. But you could imagine examples where you have much more observations, and in many cases there are as many latent variables as there are observations. So as you have more observations, the dimension of your inference problem increases similarly. So then we can't really just plug in these commonly used MCMC or kind of existing generic software packages. We can't just plug in this model and get good inference, or these type of models in general. And why is that? Basically, because there is this high dimension. MCMC is often hard in high dimension, and also there are correlations. So there is, like in the SV example, the consecutive x's are actually very, very much positively correlated, as you sort of see from this picture there. So if you want to do if you start to do Gibbs sampling, it's really, really bad. Yeah. So this is generally hard, and so these models are anyway used. So there are inference algorithms. So what are they actually doing to do successful inference on the model? Well, I want to sort of emphasize the thing that instead of treating theta and x just as a single vector, single high-dimensional vector that we simulate, we sort of want to handle theta and x in a different way. So therefore we write, or I'm going to write, I like to write this distribution basically, that we have a marginal of theta, and then I call the conditional of x with a r. Let's have r now. So that's basically just, what's important is that I want to have a factorization of the model. And then basically, if you think about it, what's the marginal here? So we know that the marginal basically, it's this is just an integral of that guy. So it's an integral proportional to an integral of that guy. So this is proportional to, this comes out of the integral. And this here is just what I call the marginal likelihood there. So this is sort of essential for what I'm talking about. And similarly, you can have the R is just basically the renormalized version of the joint, as you know. Right. So that's the model we talk about, basically. And in some sense, if you think about treating these things separately, so theta, as I said, are often low dimensional. So you might use some generic algorithm or kind of generic and non-parametric approach to approximate the distribution, the marginal distribution of theta. So you might be tempted by an idea of like plugging in MCMC for theta and doing something else for the others. But of course there are problems because you can't really calculate that integral there. So you don't have access to the marginal likelihood directly at least. But what you can do, this is what I sort of, how I like to view the current approaches, is that you either take one of the routes here. So you either basically rely on an analytic approximation, or then you basically go by kind of a tailored Monte Carlo for the latent variable part of the model. And from the first class of models, the first route is analytic approximation. So I think the most kind of widely known approach in stats, at least, that uses this, or is based on this approach, is INLA. And there are some assumptions about the model, which I don't want to go into too much. But there are certain models you can apply INLA with, but it's a big class of very useful models, so it's a useful approach. But what it does is that it relies on a Gaussian approximation, or a Laplace approximation. In fact, so I like to view it so that basically it relies on a Gaussian approximation of this joint here. And the key is that it's not a global approximation in a way. So basically, you build a Laplace approximation by fixing the theta and also fixing y, the observations. So actually, you sort of remain only with the x. But then I want to view it that you sort of approximate actually the unnormalized distribution there with a Gaussian shape thing. But anyway, you do an approximation and it gives basically rise to an approximate likelihood, similarly. Because if you have some Gaussian distribution, or, well, you have a constant there, which is the marginal likelihood. And I don't want you to focus on the formula there, but basically the central idea is that then you take a handful of hyperparameter configurations, theta 1 to theta n, and then basically you construct Laplace approximations for each of those, corresponding each of those hyperparameter configurations, and you have a weighted average to give you the output. And there are other things to INLA which I'm not going into, so, and it actually is focused on marginal distribution approximation, but if you want to view it as a joint approximation, that's what you can have. But what I want to emphasize that this is actually a sensible approach and works well in practice in many cases, but there is an approximation error there, which comes from the fact that basically you approximate this guy, which is not in interesting scenarios. It's not a Gaussian shape thing. You just approximate it by a Gaussian. So there is an approximation error coming from that, and that error doesn't vanish when you increase, if you would increase the number of points or number of hyperparameter configurations there. There's an approximation error that remains. Well, you can do in that regard better if you take the other route. And we've been hearing a lot about particle MCMC in this meeting, and we will probably hear more as well. So basically, this is the other route. So what you do is that you are going to use specialized Monte Carlo, in this case a particle filter, to the latent variable part. And this is specifically interesting when the latent variable model is a state space model or hidden Markov model like the stochastic volatility model is. And So then I don't want to go to details. Those who know the particle filter know how to calculate these variables that I refer to here. So basically, particle filter is a simple algorithm, Monte Carlo algorithm, and as a side product, you get a lot of variables out of that. And in particular, you get scalar random variables, non-negative random variables, which I call VI here, I1 to M, and then X, which are basically kind of latent variable configurations, which satisfy this kind of nice unbiasedness property, which was talked about before as well, including Pedro Moral, who I think has been sort of proving these things the first time, quite a long time ago already. Right, so I'm going to basically go in more detail to one of the particle MCMC, which is the particle marginal Metropolis Hastings algorithm. And that's basically, it is really just the Metropolis Hastings algorithm where you sort of plug in the particle filter in a nearly obvious way. And here it is sort of in detail. So if you didn't know this before, or fixed notation, because I'm going to talk about variations of the algorithm in a moment. So what you do in a single iteration of PMMH, you draw proposal of new hyperparameters from some proposal distribution that you care about. For instance, you can do random walk updates. Then, basically next, you run a particle filter with a certain number of particles, which I call little m, to get these variables, which are sort of weights and trajectories or latent variable paths. And then you do an accept reject in a specific way. And basically what I want to emphasize here is that you see our posterior distribution was like this before. Oh, sorry, the marginal posterior is like this, so it's prior times likelihood. So basically this acceptance ratio there looks very much like doing MCMC for this distribution, but this guy is replaced by this sum. Yeah, it was a hat, I think. Or tilde. But anyway, so this is basically what you do. In some sense, I was just saying that there's this unbiasedness property with the sum. So this approximates that likelihood, that marginal likelihood. But you just plug it in. It's a random variable, so you have some random fluctuations there. But anyway, so this might seem very simple, and you might think that this works roughly in a right way. But actually, this is exact, which is nice, that regardless of the number of particles, you do have consistency of the PMMH. Well, the number of particles still is an interesting quantity. It's a tuning parameter, and Mike Pitt was talking about how to tune this M well to get sort of the best balance in making the MCMC mix good enough, but not wasting too much calculations in the particle filter. Okay, so that's PMMH. And then basically, then the question one might ask, I don't know whether this is so common a question where you would ask, should I use INLA or PMCMC? I think practitioners would often use INLA if they can. That's my impression. But yeah, there may be cases where INLA might not be that accurate still. And that's actually a hard question. When do you know that INLA is good enough? Or when it might have actually a substantial bias so that you want to correct, okay? So this is sort of a discussion that goes beyond INLA. with any approximation-based method where you do, instead of Laplace, you could do other approximations. In some sense, often they work well if they are published, right? but it's hard to tell when they fail. They can fail in some cases pretty badly. Well, many of us would apply PMCMC because we like Monte Carlo. But also there is this nice theory, it's exact asymptotically. So you just keep on iterating and you should be approximating better and better what you care about. But PMCMC can also be slow and there are implementational issues there. It can be sticky, it can exhibit this kind of sticky behavior. It can stay in one state for a long time if those fees happen to be overestimated vastly at some point. Right. But basically this this paper or this route of research started from the question of how to combine ideas, how to combine approximations and MCMC or Monte Carlo in a sensible way to do this kind of inference. It's not a new question. I don't think I don't claim that at all. But I think there are some recent developments that make this tempting, even more tempting. Okay, so you could think of diagnosis of inlet output. Is there a bias, basically? That's a question you might want to answer. Or then you can think it as trying to speed up PMMH by Laplace approximations or something like that. Okay, so actually there is a direct sort of a commonly applied way nowadays how you can combine approximation or how you can use approximation within PMMH in a way that you get computational savings. And this is basically delayed acceptance. And this algorithm looks very much like PMMH, and actually the parts that are in orange there, they are sort of the differences in some sense. So actually, if you compare to this algorithm here, so you have one accept rate here. So what you do in DA, you sort of split that accept ratio in 2 bits. So actually product of these two is exactly the PMMH accept probability. And then you actually, you do 2-stage acceptance. So in the first stage, you use some approximation, say a Laplace approximation, approximate likelihood from a Laplace approximation. And you sort of screen whether your proposal is good. Your approximation should be sort of roughly what your true marginal likelihood is. So you screen whether this might be a good value. If it's not, you reject straight away and continue with the next iteration. But if you accept that, then you run the particle filter and construct the marginal likelihood estimator or all those random variables. And then you do another accept reject. This time sort of with an approximation of the desired marginal likelihood and your approximate marginal likelihood. And if everything went well, so this is expected to be rather close to 1, so you should somehow expect that you accept most of the second stage in the second stage. And what's the point of this? It's an MCMC, it's valid as PMMH. The only thing is that you sort of, this screening step can actually reduce the number of particle filter runs a lot. Can reduce up to like 70% or something, usually maybe a little less. But anyway, substantial thing. If you think about whether I run it for 2 weeks or a week, you rather choose the 1 week. So basically that's useful. That's there. Basically, what we thought about is sort of a modification of this, taking everything that is there and the repackaging. And it's sort of actually that if you if you have been doing MCMC, you might recognize already that this here looks very much like IMH, or independent sampler accept probability. And if you notice that, this comes as no surprise. So basically what you do is that this is like the delayed acceptance algorithm, the first two steps of that algorithm. So you propose and you accept or reject by the approximate likelihood, but then that's it. You go to the next iteration. You don't do another accept. You drop that. So obviously you are doing something wrong in the first phase, right? So you rely on an approximation, so that's going to be approximate. But what you can do is instead of doing the second stage in delayed acceptance, you run the particle filter only to the output of the MCMC, right? And yeah, so for all of the values of the MCMC output, you run the particle filter independently to get these guys, similarly as in DA, but basically just in a different phase of the algorithm, and then you calculate such a weighted estimator. And this here looks very much like self-normalized importance sampling. You can be a little more general. It's not just self-normalized importance sampling, but well, the ideas obviously are exactly as in self-normalized importance sampling. Right, so that's it. So then the obvious question is that, and we show basically, I'm come back to that in a second, that basically this is a valid approach as well. This is a consistent estimator. But of course the question is, what then? You know, you did a repackaging and it's valid as well, but why should you repackage your delayed acceptance, which was working quite well already? So why should you think about this kind of an implementation? Well, there is no single reason, and then there is no single reason that you should always apply this, but there are actually kind of 6 reasons why you might be tempted. So, so the first one is basically that you can do parallel computing, and what's the thing? So this phase 2 here, so this for loop here is entirely parallel. You run those particle filters independently. In contrast with the delayed acceptance, where this is a Markov chain, so you have to always run the PF if you ended up in the second phase before going there, right? So this is iterative, whereas this part here, all the particle filters can be run in a cluster if you happen to have one, or GPU or whatever, I don't know. But the point is that this is easily parallelizable, right? So that's one thing, basically, that because the particle filter often costs a lot, you may have to use quite a bit of particles to make it work, really. Here you can just use your computer cores to run those particle filters, and then you get much less kind of inference in much faster in wall clock time. Yeah, and there are other things which can be substantial or sort of interesting here. So actually, here, I said that for all of the values of the output of this chain here, you run the particle filter. Well, in many cases, this is a Metropolis Hastings, like you can be more general, but here it's actually Metropolis Hastings, and this has some positive reject probability. So you get repeated values of the same theta here. So you can actually just run the particle filter for the unique values of theta, or the accepted values of theta that come out of the chain, and construct the estimator by sort of copying exactly the output of that single particle filter for all of the repeated values. So that's the first thing. It's computational savings again. Further, basically, you can do thinning. I mean, this is all kind of trivial remarks once you do this. So you can do thinning. Thinning doesn't often make sense somehow in simple scenarios, but here, if this MCMC is rather cheap to run compared to particle filter, you might want to run this for a long time and take only kind of well, less values from the chain so that they are nearly independent, so that when you do the particle filter, you don't sort of get the MCMC mixing to affect your estimator. And you have less particle filter runs, so you save in computations. Anyway, so this can make sense. And what's more, the PMMH and the delayed acceptance version of that, they are both pseudo-marginal MCMCs. So I like that algorithm, but it has its issues. So basically, there are certain things which are not so nice about it. It can be sticky and everything. This is sort of standard MCMC, standard Metropolis Hastings. So, you know, you can do adaptation. You know how it works. If it's a random walk, you know there's much theory and everything. So that's sort of nice. And also what's nice is that that MCMC, in here, it's Metropolis Hastings. But in fact, you don't need to have this part being Metropolis Hastings. You only need to have that this MCMC targets an approximate marginal. So it's just a valid MCMC for that distribution. Can be something else. It can be also non-reversible if you believe Christoph and think that non-reversible is the future. So this is compatible with the future then. And then the last thing, which is sort of, you could think this is a bit exotic thing. So non-negativity of the estimator is also not required. So of course, in the particle filter case, as those of you who know, it's non-negative, those weights. But actually, this is an interesting direction to sort of consider sort of debiasing tricks where you get necessarily sometimes negative values as well for the weights. Yeah. So basically here is a kind of a general setup that we just try to make this clear to ourselves first, and then we try to communicate that to the others as well. But that's the other thing, how well we manage. But basically we sort of just want to do an abstraction of the thing. So we sort of go back to this thing. So we only have a factorization of the distribution. We do sort of approximate inference on the theta part, and then we correct. So what do we actually require? What's the minimal assumptions we require? And indeed, basically, it's quite easy to guess that the approximate marginal distribution has to be compatible. It has to cover everything that is in the true marginal distribution, or marginal distribution of interest. And your MCMC for that distribution has to be valid, right? That's basically there. No convergence rates or anything, just valid MCMC. And then basically, then you do conditionally independent randomization and basically generate some random variables. If you are sort of more leaning towards probability, you might want to think this as a random signed measure. But actually, it's just usually a shorthand for a weighted sum like that. So psi k of f is means just a weighted sum where f is here. This f is plugged in there, right? And then what you require is that psi k of 1, so basically you replace f by 1, so you drop that part. So the sum here, so its expected value is going to be just basically an importance sampling weight for the ratio of the marginals, right? So you sort of propose from pi a and you want to correct to pi m up to a normalizing constant that you don't need to know. And then basically for any function, you get similar thing, basically that weight, but then this is actually a conditional expectation of the latent part given a fixed theta, right? And all of this is, of course, this works out with a particle filter in an obvious way for those of you who know the particle filter literature. Yeah. So that's sort of the general stuff. So I'm just saying that we did a bit of groundwork and we wanted to make sure that what we do is first consistent, and then also that that there's a limiting law. And there's typical things, the first steps when you have a new approach. And actually, so this is consistent, basically without further assumptions that in the previous slide. And that's actually true if your weights are non-negative, you don't need more. This is automatic, this moment condition. But if you do have negative weights, you do need a moment condition. Or at least I wouldn't know how to deduce that you converge otherwise. But that's mild still. And then for the other, I don't want you to dwell on the conditions, and this is just an example, set of example conditions that gives you the CLT. You need a bit second moment and a bit of mixing for the Markov chain. But basically, you do get the central limit theorem. So if you centralize the estimator that you have to where it converges and rescale by square root of n, the usual stuff, you get convergence in distribution to a normal. And what's nice, actually, what I want to point out here is that you get this kind of a separation of 2 bits in the asymptotic variance of that estimator, kind of in this central limit theorem. So there is sort of first part that corresponds to how good your MCMC is, and that contains the mixing bits of the MCMC. So basically, if your MCMC is badly mixing, this will be large. If you thin, you can make this smaller. And this part here basically corresponds to the variability in your importance sampling correction. So basically, like in a particle filter, the marginal likelihood approximation it's often good, but it's not exact. So you have some fluctuations there. So they show up here in this part. So that's basically this could be useful somehow for understanding the approach and for tuning, but we are not quite there yet to give precise ideas how should you tune this to be optimal. Okay, and what's nice is that basically once you are sort of careful about the conditions and everything, you realize that actually the approximate chain, or the approximate marginal chain can actually be a pseudo-marginal as well, for instance. This is rather a general thing. So basically, you can do pseudo-marginal, and in some sense, everything works out just as in the PMMH. You just change your LA, the likelihood approximation, by the estimator, the corresponding estimator everywhere. But there is one thing which you should be, a word of warning, you should be aware of this. So if your estimators of that approximating pseudo-marginal, if they are not always positive, you might introduce a bias there. You can, in most cases, I think, correct the bias, but you need to be aware of this thing so that you don't, it's easy to make a mistake there. Because I sort of thought that this might work before I did the details, or Jordan did. Right, so, and this sort of connects to lazy ABC, if you know about that. So then what are the examples where we tried this out, and also kind of to give you an idea when this is relevant. So the first thing is basically the motivating part of my talk. So it's a Laplace approximations. It's a state space model, and you do particle filter correction. Or you can do importance sampling or particle filter correction. So this is actually the approximation can be done really efficiently in an iterative manner in this case. And that's basically from 20 years ago. Old stuff, but they are actually useful if you want to be efficient. You should look at the literature beyond 2000. So yeah, we do the Laplace thing, which I said, and then basically because basically you can do various things when you construct the correction. As I said, you can be rather general. So the first thing is just bootstrap particle filter. So we run a particle filter as we would do normal PMMH out of the box somehow. But that actually works pretty badly in this example. You have to have astronomical number of particles to outperform a rather simple importance sampling. No particles, just plain importance sampling. Because actually the Laplace approximation for the smoothing distribution is reasonably good in this case. So if you combine with antithetic variables, I think I was sort of struggling to outperform the simple approach by the bootstrap filter. Because I thought that particle filter should always work better than sequential importance sampling if you have that many observations. Right? But it's not always so. But then actually, if you do the right thing to incorporate that approximation within your particle filter, or do a so-called psi-APF, or Pierre would probably say that this is just change of measure and a different model, right? But which is compatible with the original one in terms of expectations. So basically, that's what you can do. And then actually then you get you outperform the importance sampling pretty much always. Right, and then we thought about, or we did experiments with a simple correction we did with a jump chain where you only run particle filter for the accepted values of the MCMC. And basically then you can compare against pseudo-marginal or delayed acceptance. Because there is a version of the pseudo-marginal and delayed acceptance for all of these as well. Or not for the first one, well, anyway, many combinations are relevant. So this is basically the results. And I want to basically highlight the ones that are highlighted there. So basically, if you think about the best way to do the correction, if you do DA, you actually get a bit better than doing pseudo-marginal, where in the pseudo or particle marginal metropolis Hastings, where you also use the approximation within your PMMH to do the twisting, right? But the DA does a bit better, and the numbers are basically inverse relative efficiencies, so they are variance, mean square error times average runtime, right? So that's basically, the lower this number is, the better your algorithm is, like generally. And you see that you get reasonable performance gain here. Not massive, right? No? But on the other hand, you don't have to do much if you had a delayed acceptance to make that IS version of that, basically. And yeah, at least you get more gain from going to DA to IS rather than going from plain pseudo-marginal or particle marginal metropolis Hastings to its delayed acceptance counterpart. Yeah, so you get gains, so it seems promising, right? Then another example which is different in a way that that basically the approximation or the approximate chain is actually in this kind of time pseudo-marginal as well. So it's a particle marginal metropolis Hastings. What's the model? The model is actually a continuous time model for the latent part, right? And then discretely observed diffusion. Discrete times when you observe in a noisy way, noisy observations of the thing. Anyway, so the point is that what we do is that we can't really simulate from the ideal model, but we can discretize. That's easy, and it's easy to simulate from a discretization. But the more discretization points you have, the denser the mesh is, the more it costs, basically. So there's a trade-off there. But what we do is that the approximation is based on a fairly coarse discretization. We only take few points where we discretize the model and do kind of preliminary inference. And then we just, afterwards, we run a particle filter with a fine enough discretization. This is really sort of a naive thing to do, but it's a nice example. So in that case, actually, and then we did in this case, in the previous example, there was no parallel aspects involved at all. So it's just plain cost in a single thread. But this was a parallel implementation with 48 cores. And actually then you get the reasonable gain. And I don't want to go into details. So there was actually there is a burn-in issue with the delayed acceptance here. But basically that's another thing. What I want to sort of advertise here is that instead of doing the second phase to a fine enough mesh, you can actually randomize what's the level of discretization you do and calculate a clever difference there and then do a bit of correction, and you actually get exact inference in the end to the ideal diffusion, which corresponds to the ideal diffusion. But there's actually going to be a detailed presentation in the closing workshop, so let's leave that there. Okay, so then basically a bit of discussion. So there's a question. Does someone want to guess what's the answer for this question? So is it always better to do IS in comparison with DA? You say yes? Yeah, the answer is no. I like this part. Thanks for joining in. Yeah. So there are actually details in a few weeks again, but I can tell a little bit about it. Yeah. So basically, drop the latent variable part. It's just like just thetas, and this is a simple example. So your pi m is here. You do random walk proposals, and basically dA would sort of be contained all the time here. So you have a uniform distribution here as being the marginal, whereas your approximate marginal is here. So your importance sampling counterpart, the MCMC, would go around everywhere, and then basically the weights would be zero everywhere else, except for here. So you can imagine that it's much worse. Yeah? So this is bad news. We can actually be much worse. But it can be the other way around as well. So that's nice. So if we just modify the example and add another mode there, actually the dA would be reducible. It wouldn't be able to jump from one node to the other. And you can, of course, make it irreducible, but really bad as well. But basically, the IS would outperform it by any factor you want. So in some sense, no clear answer. But actually, in practice, you don't have anything like this. You have approximate. You have approximation. So pi m should look about the same. And our experiments suggest that basically it seems to perform better in practice, right? But not always. And I'm not going to the details because there's the talk in 2 weeks, right? But rather wrap up. So basically, well, I suppose the take-home message is if there's an approximation, use it, right? So don't forget that. I think practitioners usually know about this, but maybe we are a bit lazy many times to use that. We think this is a natural way to use the approximation within thing. And basically where you can apply dA, you can easily try this at least as well. And we've done a bit of contribution, and there is still ongoing work as well. So thank you.
The argument I had for importance against delayed acceptance is that if you are looking at approximating intervals in only that aspect, there's always a gain to avoid the final randomization of accepting or rejecting. So for instance, if you compare accept reject and impulse sampling only for the variance of your estimators, there's always a gain in doing directly impulse sampling rather than accept reject.
I don't think so, actually.
Really?
I think there's I think yeah, we can actually go through this on a, some point later, but not now. I think there is a, generally I think the story is like that, but I think it's not quite mathematically a solid statement to say even the rejection sampling versus importance sampling. It's not always so. Number of yeah, you mean proposals. Yeah, no, exactly, that's what I was thinking, but I think yeah, we can discuss about this later, but I think, yeah, yeah.